attraction, or IMFs for short. Intermolecular forces of attraction are only for covalent molecules. So, molecules that contain only non-metals. Intra means within. Inter means between. So these are forces of attraction between neighboring molecules. An example of an intramolecular force would be a regular covalent bond. Intermolecular forces are actually quite unique when you look at them. So if you have a scale from 0 to 100, where 100 is the strength of a covalent or ionic bond, the strongest intermolecular force is about 10% of that, and the strongest one is hydrogen bonding. Now, it's not a natural bond. It's not a natural bond. It's an intermolecular force of attraction. No electrons are transferred, and it's about 1/10. So there we've got our H bonding. The next strongest one that we're going to look at is dipole-dipole. You have dipole-dipole if you are a covalent polar molecule. So if you're polar. A hydrogen bond is an extremely polar bond, but it can only happen if you contain an OH bond, an NH bond, or an HF bond within your molecule. The weakest, like right down here close to 0, the weakest is London dispersion forces. Or LDFs. All covalent molecules have London dispersion forces. That's because they have protons and electrons. So what it is the attraction of one molecule's protons for the electrons in a neighboring molecule. The strength increases the more electrons they have and the more protons. So the more protons, electrons, so the higher the atomic number they have. So if we compare H2 and F2, hydrogen molecules have 2 protons, 2 electrons. Fluorine will have 18, 2 from each. There's 2 fluorines, so 2 times 9 is 18. Therefore, the London dispersion forces between fluorine molecules in a container are going to be stronger than the London dispersion forces between hydrogen molecules in a different container. The result of this is that fluorine will have a higher boiling point than hydrogen. It takes more energy to disturb those forces to separate the molecules from each other. In order to decide if your molecule has dipole-dipole or not, you have to decide if the molecule is even polar. If it's not polar, it won't have dipole-dipoles. So, there's two groups of substances that I want you to remember that are non-polar. It's easier to remember the non-polar than all the ones that are polar. So, if you are a diatomic element, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine, your difference in electronegativity is 0 because you're bonded to the same type of atom. So these are going to be nonpolar. The other type of compound that you're going to come across that's nonpolar is carbon bonded to some other atom, and it's only one type of atom, and you have an even number of atoms of that element. They will also be nonpolar. So carbon dioxide, carbon's only bonded to oxygen. There's 2 of them. That's an even number. So this is nonpolar. Carbon monoxide, one other atom, but it's an odd number. It's 1. So this is polar. CH4, one type of atom, even number, nonpolar. CH3Cl, more than one other type of atom, hydrogens and chlorines, so this is polar. Everything else will be polar. So if you have a polar molecule, you will have London dispersion forces and you will have dipole-dipole. So your boiling point will be higher than something that has just London dispersion forces. Okay, then there's the last one, hydrogen bonding. If you have hydrogen bonding, you have an even higher boiling point because the forces of attraction are even stronger. So, if you contain an OH bond, like water, and this would be your hydrogen bond right here, then you will have an even higher boiling point because those forces of attraction are really strong compared to dipole-dipole. This is basically an extreme dipole-dipole. So for your homework, let's say question 2. B, Cl2O, dichlorine monoxide. Intermolecular forces that happen between molecules of this. This isn't a diatomic element. This isn't carbon bonded to something else, so it's polar. So it has London dispersion forces and dipole-dipole. Okay, question 3. Start you off. If you look at these, you have to decide if they are polar or non-polar. So I'll do 3 of them for you. So first one. This is non-polar. So it will only have London dispersion forces. It's nonpolar because it's carbon bonded to one other element, and there's an even number. The second one, C3H8, also nonpolar, also has only London dispersion forces. One other element bonded to carbon, and there's an even number of those hydrogens. Last one, NH3. This isn't carbon. This isn't a diatomic element, so it's polar. It's going to have London dispersion forces and dipole-dipole. But if you look at it, it also contains N bonded to H. So this will also have hydrogen bonding. So if you had to rank these in terms of boiling points, this one's definitely going to have the highest because it has the strongest intermolecular forces, keeping the particles together. To compare these two, they both have London dispersion forces, but there's more elements in C3H8. So therefore there's more protons and electrons, so it has stronger London dispersion forces. Therefore its boiling point is higher than methane. So methane will be your lowest, propane is middle, and ammonia is highest. I hope that helps.